rectifying AC input as shown here. This section rectifies AC input and feeds a DC to three-phase inverter bridge. Hall sensors are used for commutation in this example. These three Hall sensors are connected. They can be either connected to interrupt pins into 0, into 1 and into on PIC18Fxx31. In this case, I have taken an example of 18F2431, a 28 pin member of PIC18Fxx31 family. The Hall sensors also can be connected to the input capture module here, which is configured as input capture, the motion feedback module, which is configured as input capture, IC1, IC2 and IC3. The input capture module has a mode in which the module generates an interrupt on transition on every pin, making it ideal for Hall sensor interface. So optionally, with this, timer 5 can be captured on each transition. This timer 5 value can be used for determining the speed at which motor is running. This gives a low resolution speed measurement. Using timer 5, we can determine at what speed the motor is running, and this gives a low resolution speed measurement using Hall sensors. In this case, motor current can be measured using feedback devices. Motor current measurement devices may be a shunt resistor connected in series with the return path on DC bus, and can be connected to ADC channel or analog to digital converter channel here. Also, motor current can be compared with a fixed reference here using an op-amp comparator, and a fault condition can be generated if the motor current exceeds this reference. This fault can be monitored using the fault pin, which is connected to one of the pins here shown as fault A pin, which will shut down the PWM in the event of overcurrent condition. A potentiometer. In this example, I have taken a potentiometer in order to give a speed reference or speed command to the microcontroller. The speed command can also be digitally controlled or digitally input from a PC or another master controller interface to UART or SSP module. For the applications where high resolution speed measurement is required, quadrature encoders can be used. This we will see in coming section how a quadrature encoder can be interface with the PIC18Fxx31 family. Now let us see how PWM can control the motor, or how the speed can be controlled using PC PWM module. PC PWM module has a feature of overriding the PWM outputs based on the value in a register called OVD-CON-D or override control register. When the corresponding value in OVD-CON-D is set to 1, the PWM output becomes active, and vice versa. When the bit in OVD-CON-D register is set to 0, the PWM becomes inactive. With this, we can efficiently control the required PWMs to appear on the pin when required, which is as per the sequence, or inhibit when it is not required. So, looking at the previous slide, the first sequence with when the Hall sensor input is 101, we saw that switch H3 and L2 should be active. In order to make these two PWMs active, or these two switches to come active, PWM5 and PWM2 should be put to active state. So the OVD-CON-D register is set with 1 at 5th position and 1 at 2nd position here, which makes PWM5 and PWM2 to be active during that period. So when the Hall sensor input changes to 001, OVD-CON-D register is set with the required value, which should make PWM2 and PWM1 active here. So on and so on. If we load OVD-CON-D register accordingly, the sequence will be followed. Speed variation is achieved by varying the duty cycle of each PWM. To increase the speed, the active part of the duty cycle here need to be increased, and to reduce the speed, the active time is reduced. By doing this, The average voltage applied across the motor winding varies, controlling the motor speed. This slide shows the relationship between OVD Conti register and PWM outputs, which are controlling the 6 switches. So the PWMs are passed and inhibited according to the sequence discussed earlier. Next, let us quickly see how a control flow chart looks like. This is a simplified flow chart controlling a brushless DC motor. The sequence table dictates the PWM channels that should be active or inactive state here. So this is the same table that we have seen earlier. On every transition of Hall sensor input, new step from the sequence is loaded to OVD Conti register. So Hall sensor input is monitored every time, and if there is any change in Hall sensor inputs, new value to OVD Conti register is determined and loaded. And any change in speed command is read either using a potentiometer, as we have seen earlier, and a new PWM is calculated. A new PWM duty cycle is calculated and loaded to the appropriate registers, the duty cycle registers. Other applications also can be interfaced, like key scanning to control the direction of rotation, or to control start and stop of the motor, or other applications can include LCD interface or 7-segment LED interface, etc. So till now we have seen controlling a brushless DC motor using Hall effect sensors. Next, let us see how we can control brushless DC motor in closed loop using quadrature encoder and using a motion feedback module to interface a quadrature encoder inputs. This slide shows how quadrature encoder can be interfaced with the PIC18Fxx31. A quadrature encoder is mounted on the BLDC motor shaft, and the signals A, B, and index are interfaced to the motion feedback module here. This quadrature encoder interface gives high resolution speed measurement, and also it gives position and direction feedback. In this case, Hall sensors are used for commutation. So these Hall sensors are connected to interrupt pins int 0, int 1, and int 2. And all other hardware description holds good as before. We have seen how 6 PWMs can be interfaced to control 3-phase inverter bridge, and how motor current can be compared and generated a fault input to shut down the PWM in case of any overcurrent situations.